Happy New Year!
Well, yeah, Happy New Year, guys. Welcome to 2013.
Yeah, welcome to the new year. Speaking of bright and shiny things.
Which it's not. It's dark out. Go ahead.
Yeah, but it's a bright and shiny new year.
True. That is true.
Yeah. Like Rudolph's New Year.
Yeah.
Yeah. We're going to be discussing the nature of light and why things give off light.
You are going to be knowing what is meant by the dual nature of light. You are going to be able to describe the electromagnetic waves in terms of frequency, wavelength, and speed. Identify regions of the electromagnetic spectrum. Distinguish between continuous and line spectra. State main ideas of the Bohr's model of the hydrogen atom. And you're going to be able to calculate the frequency, wavelength, and energy of a photon of light. You're going to be able to describe the process by which atoms emit photons of light.
So, as a quick review here, the last time we saw the atom, okay, so Rutherford's model looks like that picture in the corner there. It's not quite drawn to scale, but the model of the atom currently is made up of mostly empty space. The atom is spherical in shape, generally. Rutherford had coined the term nucleus, which he designated as the small positive center.
This is the guy who had the grad students do all the work, right? Gold foil experiment?
Correct.
Okay.
Yeah. So he's got the small ball of positive charge that is the nucleus. We've got protons and neutrons in the nucleus, and we've got these electrons that are moving around the nucleus. The detractions of Rutherford's experiment. He didn't explain how the electrons were arranged. They were just kind of moving about the atom. He couldn't explain how electrons were not pulled into the nucleus.
Yeah, because if they're orbiting the nucleus and the nucleus is positively charged, aren't they being attracted? So why aren't they all just crashing into the nucleus?
Yeah, exactly. So there was no explanation there. And we needed more information to shed some more light on the atomic model.
Oh, that's very funny.
Unit 11 light.
Yes, get it.
All right. All right, so speaking of light.
All right, electromagnetic radiation. It's a generic term for light, so all light is part of the electromagnetic radiation, right? And light is anything we see or feel.
Right. All electromagnetic waves move at the same speed, okay, which is the speed of light.
Okay.
Okay. Which we need to know this.
Okay.
All right. 3 times 10 to the 8th meters per second. Or in chemistry, we more often use 3 times 10 to the 17th nanometers per second, because we're talking about really small stuff, right?
So that's going to be a constant, isn't it?
That is going to be a constant.
7 parts to electromagnetic radiation, the electromagnetic spectrum.
Okay, so the electromagnetic radiation includes light.
Yep, some we see and some we don't.
So it includes things like gamma rays,
X-rays,
ultraviolet,
visible light,
infrared light,
yep,
microwaves, and radio waves.
Radio waves.
Okay. All of these have different wavelengths and different frequencies and different energies.
Now the way I've listed them here, it's high energy because of course gamma rays nothing stops gamma rays.
Yeah, well, the Hulk stops gamma rays.
Yeah, the Hulk stops gamma rays. X-rays.
So high energy and then lower.
Going lower until you get to microwaves, and radio waves are the lowest energy waves.
So radio is the lowest. So if we wanted to actually write this out in a continuum, we'd write it out
that way.
That exact order.
Now, here's a tricky question, Mr. Kane. Only one portion of the electromagnetic spectrum is visible to the naked eye. Guess which one it is.
Ooh, I know. It's got to be visible.
Visible light.
Only thing that we can see is visible light.
The only portion of the electromagnetic spectrum that's visible.
Huh. Interesting.
Isn't
so I can't see infrared?
No, you can only feel
it. So when I go to McDonald's and they have those infrared lamps on my burger to keep it warm, that red light that I see, that's not infrared?
No, that's infrared, but the bulb is a red light too.
Okay, all right, okay.
If you put your hand under it, you'll feel the energy.
So it's got both kinds?
Yeah.
All right, okay. So these are shorter wavelengths down here, so things that are shorter wavelength are like gamma rays.
Correct.
And 10 to the 13th, that's really long.
That's a long wave.
So long wavelengths include things like radio waves.
Yep.
But the frequency isn't the same. This is a high frequency, right? 10 to the 20th?
Yeah, that's a big number, so frequency's opposite.
That's high frequency, and this is low frequency.
Okay. So they're opposite to each other.
Right, they're inverses.
Yeah.
Ooh. Oh, hey, check out this little portion that's visible light right here.
Just a smidge that we can see.
Just a smidge that we can see, and they kind of exploded it here to be much bigger. So we can see from 400 nanometers to 700 nanometers.
Yep.
But it covers this huge range from 10 to the negative third nanometers to 10 to the 13th nanometers. Why can't we see that stuff?
Well, it's just part of the other parts of the spectrum that you can't. You just feel.
Okay.
Too. On the visible light, that has short wavelengths, long wavelengths too, doesn't it?
Oh, yeah.
Right? Is it 400 nanometers versus 700? That's a short wavelength compared to 700.
Short versus long. Yeah, the longest wavelength of light is red.
Yeah.
And the shortest is violet. Yeah, we'll give you a handout on the visible light range also, so you don't have to copy that down.
Yeah, okay.
Okay. Although I do see my good friend Roy G. Biv there.
Yeah, just kind of a little backwards.
Yeah, just a little backwards.
So if it's Roy G. Biv, then it's Vib.
Y, G, B, I, and then finally the darkest color of purple is
So from left to right, from low short wavelength to long wavelength, it's Vib G Yor.
I guess so, yeah. And the way I always remember it is Roy G. Biv, but okay. All right, properties of an electromagnetic wave, like we talked about before.
So a wave has properties. All right.
Waves have properties. They have length, and we call that length wave length. And the definition is the length of the wave.
Yep.
Usually use meters or nanometers. More typically in chemistry, we use nanometers. Okay.
And that's usually measured from like peak to peak, right?
Peak to peak.
Yep.
From the top of one wave to the top of another wave.
Yeah.
Yep. And this is the Greek symbol lambda.
Okay.
Because that's what we use to measure, to show wavelength when we want to.
I gotta learn, I don't know my Greek. I never remember.
It's all Greek to me. All right. And here is the Greek letter nu.
All right.
It looks like a V, but it's got this little bit of a, it's got a little bit of a, we draw it like
cursive.
that. Yeah. Okay, it's kind of like a cursive V.
So those are the symbols for wavelength and frequency, or are those the units?
Those are the symbols
Okay.
for them. So if we want to use them in a equation, like we use N for number of moles, and we use T for temperature,
So
we use lambda and nu.
All right, instead of writing out wavelength, we use that funny looking,
yeah.
looks like an upside down Y to me, but.
Yep. All right, but frequency is the number of waves per second. So it's how often a wave would hit something.
How frequent.
Okay, how frequent, exactly. And it's measured in units of per second.
Okay.
Or seconds to the negative 1 power. So if you remember your algebra class, you remember that both of those say the same thing.
And there's a third one I'm familiar with.
Yes. It really hurts
yeah?
here because there's a lot of different units for frequency.
Is that how you remember it?
Yeah, that's how I remember it.
Yeah, that works.
Hurts, okay.
Because I see a computation coming up here, Mr. King.
Oh yeah, there's a computation coming up.
All right.
All right, so putting it all together.
I told you there was a computation coming up.
Yep, look at that. There is a relationship here, a mathematical relationship between C, lambda, and nu.
Okay.
And it's sometimes misunderstood when we don't write the symbol, but it's C equals lambda times nu.
Okay.
Okay. So the wavelength, so the speed of light is always equal to wavelength times frequency. And the fun part about this is that you just said that the speed of light is always a constant.
Yeah.
It's always either 3 times 10 to the 8th meters per second, or 3 times 10 to the 17th nanometers per second, depending on whether we want to measure wavelength in nanometers or meters.
Oh, well, that makes it easy then, because that's 3 variables, and one of them's a constant. That means 2.
One of them's a constant, so we'll always be able to measure a frequency or a wavelength, and we'll want to calculate the other.
All right, so given frequency, get wavelength. Given wavelength, get frequency.
Then you want to find frequency, right?
Yeah, let's say that.
So I want to divide both sides by wavelength in order to find frequency. So the new equation would be C over wavelength equals nu.
Okay, now what if we wanted to do wavelength?
If I wanted to do wavelength, I'd have to divide both sides by nu, and I'd get C over nu equals wavelength.
Okay. We're going to do some examples right now.
Okay, so you've got an electromagnetic wave with a wavelength of 760 nanometers. This is probably telling me that I should use a speed of light here of 3.00 times 10 to the 17th nanometers per second, because that's in nanometers.
Right, and you want units to cancel because you want frequency to be in per second.
Might as well show that.
Yeah.
So let's see. We just said that the equation was going to be c over wavelength is equal to frequency, right?
Yep.
So that means that I'm going to put 3.00 times 10 to the 17th nanometers per second, and I'm going to divide it by 760 nanometers.
Which is 3 sig figs. Don't forget your decimal place.
Oh, the decimal place. Yes, you're right. There's 3 sig figs there. So
You're going to get a 3 sig fig answer.
all right.
It's going to be 3.95 times 10 to the 14th
Can't forget that.
per second.
Yeah, notice nanometers and nanometers cancel, so I get per seconds
You're
here.
literally left with per second.
Can I put hertz?
Yeah, you could put hertz.
Okay, hertz. You're literally left with per second, but per second is hertz.
Okay.
Because we usually explain frequencies in hertz, right?
That's a pretty big...
That's a pretty big frequency. So
Yeah.
that means that with this particular wavelength of electromagnetic wave, when you get hit by it, you're getting hit 3.95 times 10 to the 14th times per second.
Yeah. Yeah.
That's a lot of times to get
That's
hit
a
by a
lot.
wave.
Then it's kind of funny, too, because 760 nanometers, that's just around the red.
Yeah, that's right around red wavelength,
Yeah,
the light,
so
isn't
that's got to be in the infrared range somewhere to the red light.
it? Long wave.
All right, another one, another example. An electromagnetic wave
Length
of length
2
of
meters.
2 meters. What is the frequency?
2 meters is about as long as my desk at school.
Yeah. Pretty short.
So let's see what we're going to do here. Frequency is equal to c over lambda. C is 3.00. Since this is meters, I should probably use meters, huh?
Yeah, I would
Times
suggest
10.
you use that.
So times 10 to the 8th
Yeah,
meters per second.
yeah.
Divide by 2 meters, and we get 1.5 times 10 to the 8th
Yep,
hertz.
per second. Yep.
Yep, per second. Because meters and meters canceled, so that's hertz. That would really hurt if somebody hit me that many times a second.
Yeah. Okay. In light, what is the relationship between wavelength and frequency?
And we've already started we've already started talking about this, but
They're opposite.
yeah, that they're inverses. So red light has long wavelengths, red light has short frequencies.
Okay.
So long wavelength, short frequency.
And that was at the red light was the it was the 700 nanometers area.
And it turns out that red light has less energy.
So frequency and energy are the same,
Okay, when
or
you're
equivalent, I should say.
yeah, frequency and energy are similar.
Okay.
Now violet light has shorter wavelengths, and they use that in tanning beds.
That was at the 400 nanometers. So yeah.
It has higher frequencies and more energy because it's got higher frequencies. It's hitting more often.
Well, is more energy more penetrating? Because aren't gamma rays more penetrating than X-rays?
They tend to be, yeah.
Yeah.
Yeah, more energy tends to get you farther through the human body
Okay.
or anything else.
And ultraviolet light, that's the sunlight, yeah? Is sunlight considered ultraviolet?
There is some ultraviolet and
Yeah.
sunlight that gets through
They're
the
always
ozone
talking
layer.
about UV light. So if
Yeah.
they're sitting in a tanning bed under violet light, that's about the same thing. They're next to each other on the spectrum.
UV and gamma?
Yeah, no, UV and violet light.
UV and violet, yeah. They're pretty close.
So tanning bed or sitting out the sun, you're doing the same damage. They're just as penetrating as each other.
It's the same thing. UV is
All right.
UV.